In this video, we're going to compute some more integrals. The title of the section is Further Transcendental Functions. Really, that's just a fancy word. Transcendental means that they transcend algebra. These are functions that aren't polynomial functions, things like exponential functions, log functions, and we're also going to talk about inverse trig functions. So to talk about integration of these transcendental functions, first we're going to review, well, what are the derivatives of each of these functions? And if you'd like a more explicit explanation of the derivatives of these, I'll have some links to some further videos at the bottom of the page. Recall that the derivative of e to the x is e to the x. It's the self-replicating function. And also recall, this was even in a previous video, that the derivative of natural log of x is 1 over x, given the right domain values for x. So this information tells us that we now can compute the antiderivatives, or the integrals of each of these functions. Working backwards by the fundamental theorem of calculus part 2, we can say that the integral of e to the x dx is going to be equal to e to the x plus c. And we can also say, working backwards, that the integral of 1 over x dx is going to be equal to the natural log of x plus c. And keep in mind, there is the restriction that we want this to be the absolute value of x, because that's the only place that natural log is defined, is on positive values. So let's use this for an example. Suppose I want to integrate the following function. Suppose I have the function x squared times e to the x cubed plus 7, and I want to take the integral of that. A naive person, or something that's a common error to make, is to think that, aha, this is a product. I can take the integral of this piece, and I can take the integral of this piece, and just multiply them together. And that's incorrect. Warning. Can't integrate each factor separately. See how I wrote that in bold font? That's so that you won't ever think that you could just integrate each of the pieces separately. In this case, we're actually going to need to do a U-substitution, and we have a nice U-substitution that we're able to do. I recognize the fact that I have a composition of functions over here. I have e raised to a function of x, and it turns out the derivative of this function, well, most of it is sitting right here, so this is a great candidate for a U-substitution. I'm going to let u equal x cubed plus 7, and that means that du is the derivative of this, which is 3x squared plus 0 dx. And thankfully we have most of the pieces sitting here already. We have a dx, we have the x squared that we need to make the u substitution, but we don't have a 3, so I'm going to go back to my original integral. I'm going to multiply it by 3 and also multiply it by 1/3. That doesn't change the value of the integral at all, because I just multiplied it by a clever version of 1. And now I can use those new pieces, maybe I'll rewrite it down here, 1/3 times the integral of 3x squared times e to the x cubed plus 7 dx. All of these pieces together, the 3x squared and the dx, are going to combine to make my u for my u substitution. Which means I can rewrite the value of this original integral as 1/3 the integral of e. This whole exponent was my u substitution, e to the u du. Now that I've done the u substitution, I integrate. It's an easy integral to compute, because the integral of e to the u is just e to the u plus c. And then my final step, I don't want to leave it in terms of u. I'm going to plug in my original u as my function. This becomes x cubed plus 7 plus c. If If you'd like, you can always check to make sure that this was in fact correct, and I don't do this that often and I should do it more. I took this integral and I came up with this. That means that I should take the derivative of 1/3 e to the x cubed plus 7, and I should get back my original integram function, the interior here. Let's check and see what happens. The derivative of e to the stuff is just e to the stuff. The coefficient just comes along for the ride. But by chain rule, I have to make sure that I multiply by the derivative of that exponent. The derivative of x cubed plus 7 is 3x squared. And notice you see where the 1/3 and the 3 is coming from within chain rule. This simplifies to be e to the x cubed plus 7 times x squared, which is indeed what we wanted. So that's a nice review of what a U-substitution looks like. Let's look at another transcendental function. Let's look at the derivative of 2 to the x. One of the things, here's another warning, an error that I see a lot, that taking the derivative of this, some people say, oh, I know what the derivative is, I can use power rule, I'm going to subtract 1 from the exponent and say that the derivative of 2 to the x is going to be 2 to the x minus 1, and I'm going to multiply that x minus 1 out front, right? But I say warning because that's not the case. It's not the case because this is not a polynomial. I can't apply power rule when I have a variable in the exponent. And that goes for derivatives and integrals as well. So common error, don't make that error. Instead, we're going to have to be a little bit clever, and I'm going to do some thinking off to the side about cleverness. I don't know what the derivative of 2 to the x is per se, but I do know what the derivative of e to the x is. And I'm going to rewrite 2 in a really clever way. I'm going to rewrite 2 as e raised to the natural log of 2. Why is e raised to the natural log of 2 equal to 2? Well, that's what a log is. A log is asking e raised to what value gives me 2, and I'm raising e to that value. Maybe that's a complicated sentence, but this is my clever trick. So now I can use a property of exponents and say e raised to a power raised to another power is the same thing as e to the natural log of 2 times x. So that means that, going back to my original derivative, the derivative of 2 to the x is equal to the derivative of e to the natural log of 2 is just a constant. It's just some number. I could plug it into a calculator, 1 point something 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 stuff. So the derivative of this is going to be, by chain rule, e to the natural log of 2 times x times the natural log of 2, because the derivative of the exponent is just going to be the derivative of the derivative of 4 times x is just 4, so the derivative of natural log of 2 times x is just natural log of 2. And now, undoing my clever version of 2, I see that this is 2 to the x times the natural log of 2. Maybe that was a longer excursion than you were interested in seeing, but I think that it's helpful. I think it's a good review of exponent laws as well. So why did I do all of this work? We just decided that the derivative of 2 to the x is equal to 2 to the x times the natural log of 2. And this is something you might have memorized as well. What does that mean for the integral of 2 to the x? It means working backwards. If I were to integrate this side, it's not exactly this side that I'm integrating though, right? Because I'm taking this constant. I just want to look at what is the integral of 2 to the x, and it would bring me back here. It means that the integral of 2 to the x is going to be 1 over the natural log of 2 times 2 to the x plus c. And let's check this. We can check this by taking the derivative. The derivative of this side is going to be 1 over the natural log of 2, maybe I'll write this out explicitly, the derivative of 1 over natural log of 2 times 2 to the x is going to be, well, we know what the coefficient is. The coefficient just goes along for the ride. And the derivative of 2 to the x is 2 to the x times the natural log of 2. These natural logs cancel each other, and indeed, we get back what we started. The final piece that I want to talk about for transcendental functions, non-algebraic functions, are inverse trig functions, and this is something that is a little bit complicated. If you want to look up the derivation of each of the derivatives of these inverse trig values, you can go to the links at the bottom of the page. Instead, we're going to use these identities. These are some of the few things that I think are valuable to memorize for this class. And using this information, that the derivative of inverse sine of x is equal to 1 over the square root of 1 minus x squared, that gives me the information that if I were to integrate both sides using the fundamental theorem of calculus part 2, I get that the integral of the right side, 1 divided by the square root of 1 minus x squared dx, is going to be equal to the inverse sine of x plus c. And that holds for these other identities as well. That if I wanted to integrate any of the right side values, it will give me the input function of the left side. This is really helpful, except for the fact that most of the time when I'm looking at integrals, I don't have a really nice 1 minus x squared or 1 plus x squared situation. Let's look at a pretty complicated example of one of these inverse trig derivatives. So suppose that I wanted to integrate from 0 to 1 of 1 divided by the square root of 4 minus 3x squared. Looking at this table, looking at the identities we just talked about, this is really similar to what we have for the integral of inverse sine. The problem is that I don't exactly have a 1 here, and I also don't exactly have an x squared here, that this whole term isn't being squared, only the x part of the term is being squared. So we're going to have to do both some algebra, and we're also going to have to do a U-substitution to be able to use this property. So to start off, I'm going to start by trying to get a 1 as the isolated term. And how am I going to do that? The first thing that I'm going to do is I'm going to factor out 4 from each of the terms in the denominator. If I factor out a 4 over here, I end up with 1. And if I factor out a 4 here, this is a weird way to think of it, I'm going to be left with 3/4 x squared. Let's pause for a second and see what I just did. By the distributive property, if I were to multiply 4 by each of the terms in the denominator, I would get 4, and I would also get 4 times 3/4, which is 3. I get the 3 back again. And I did this so that I can get a 1 here. Using some more algebra, I'm going to use some more algebra. The denominator I can rewrite as the square root of 4 times the square root of 1 minus 3/4 x squared. And I'm allowed to do this because this square root applies to both of the factors. That this is the square root of 4 times this big messy thing. That's the same thing as the square root of 4 times the square root of this big messy thing. And now this is just a constant that I can pull out front. Nice. 1/2 times the integral from 0 to 1 of 1 over the square root of 1 minus 3/4 x squared dx. Awesome, we're well on our way because we know that we need to have a 1 as the linear term here. We factored out the 4 to be able to get this as a 1. The next thing is that we're going to do a variable substitution. That my final form, the way that I want it to look, maybe I could look at my cheat sheet again, is I want this whole thing to be some sort of x squared. And we're going to have to do a U-substitution for that. So I want my U to be equal to this piece. No, I don't want it to be U, do I? I want it to be U squared. So this is what I'm thinking to myself. This is sort of my preliminary steps to get ready for my actual U-substitution. I want this whole thing to be a U squared. So let's set it as a U squared. What does that mean that U is equal to? That means that by taking the square root of both sides, we see that U would be equal to the square root of 3/4 x. And I can rewrite that actually as U equals the square root of 3/2x, the square root of the numerator divided by the square root of the denominator. Aha, so this is the U substitution that I want to use. And let's check. If I were to square this, I see that U squared is equal to the square root of 3/2 x squared, which is indeed what we want it to be, the 3/4 x squared. Cool. So this is the U substitution that I'm going to use. I need to find out what my du is. Du is going to be equal to the derivative of this, square root of 3/2 dx. And I don't have all of those pieces exactly here. Notice that I don't even have a square root of 3/4 x necessarily. I'm going to do one interim step to make sure that my algebra aligns. In the denominator, I want to make it 1 minus something squared. And what is that something? Well, it's U, or it's the square root of 3/2 x. Right, so this is my preliminary step before I do the U substitution. Now in order to do the U substitution, I have a dx, but I don't have a square root 3/2, so I'm going to have to multiply by square root 3/2. Maybe I'll multiply it by square root 3/2. If I do that on the inside, I'm also going to have to multiply it by 2 over the square root of 3. These pieces become my dx, or du, and I'm left with 1/2 of, recall these bounds are when x goes from 0 to 1. Again, not standard notation, but notation that I always use, that I like. The 2 over square root 3 has to stay there. The square root of 1 minus U squared, this piece becomes my du. I'm going to do one more algebra step. This is 1/2 times 2 over the square root of 3 times the integral from 0 to 1 of 1 over the square root of 1 minus U squared du. Phew! So all of this work has gotten us to the point that we have this nice U substitution. These 2's even cancel. And I can go ahead and integrate. Thankfully, I'm actually not even going to take a new page. I'm just going to continue right up here, because this last piece, oh, I'll take a new page. I should give myself space. This last piece is actually sort of nice. I'm left with 1 over the square root of 3 times the integral as x goes from 0 to 1 of 1 over the square root of 1 minus U squared du. The whole reason why we did all this work was because we have knowledge of what this integral is. This integral is just the inverse sine of U. Right? That's what our identity is. And x is going from 0 to 1. Notice that these variables don't match, so this is my sneaky notation. I know that before I can plug in the bounds, I'm going to have to go back and replace u with x. So in this case, let's look back. U was equal to, I guess here is a better place, u is equal to the square root 3 over 2x, evaluated as x goes from 0 to 1. Let's go ahead and evaluate these bounds. This is 1 over the square root of 3. When I plug 1 in, I get the inverse sine of square root 3 over 2 minus 1 over the square root of 3 times the inverse sine of 0. I have to use a unit circle. You could use a calculator. I think it's more clear for me to think about my properties of the unit circle to figure this out. Remember that sine is the y value of the points on the unit circle, and I know that I get a y value of 0 at an angle of 0. So that's telling me that the inverse sine of 0 is 0. This piece, I want to know what angle do I plug in to get a height of 3 pi over 2. I know that this point right here is the point 1/2 comma square root 3 over 2, and that point happens at an angle of pi over 3. So that tells me that the inverse sine of square root 3 over 2 is pi over 3. And so my final answer for this integral is pi times 3 over times the square root of 3. And if you're being precise about things, something that's nice to do is to clear the radicals out of the denominator by multiplying the denominator and the numerator by square root 3. So I'm going to do that, and it means that I end up with square root 3 pi in the numerator, and I end up with 3 times 3, which is 9, in the denominator.